guys, and welcome to one more episode of Builder Nation. For today's agenda, we have Professor Karol Miller, all the way from Australia. He's a specialist in the area of modeling and computer simulation in biomechanics and director of the Intelligent Systems for Medicine Lab at the University of Western Australia. Welcome, Professor. Super excited to have you here.
Thank you so much for having me. I am Karol Miller, born and educated in Poland. I am sure you can hear the accent. By education, I am an aerospace engineer, but in most of my career, I worked in biomechanics and robotics. So after completing my PhD in Poland, I went to work in Japan. For the government for government labs there, and after a few years in Japan, I moved to Australia, and I've been in Perth, the University of Western Australia, for now 26 years.
So you've been living in Australia for a long time now. And how long did you stay in Japan? That's really cool.
2.5 years initially, and then a number of stays of half a year. I have still a very active collaboration with Japanese government research.
Nice. And that was before or after you started the laboratory?
This was before. I started the lab in 2002, so 20 years ago, and my stint in Japan was in before that, in the 90s, late 90s.
Now I'm really curious. I mean, you're an engineer, right? And how are you like, okay, I'm gonna start working with intelligent systems?
So my master's was in biomechanics, PhD in robotics, and doctorate of science again in biomechanics. And wherever you look, wherever you turn your head, now you have essentially mechatronic systems around you, right? So there is a car, a fridge, a phone, everything is a mechatronic system. Combination of mechanical engineering, electrical engineering, and computer engineering or computer science, right? So essentially everything is intelligent, but to some extent. But the story for the name of the lab is very funny. I drank vodka with a very famous professor from Texas, Delabert Tesar. And I asked him, okay, I am starting the lab. What should be the name? And he says, oh, must have intelligent in the name. And it must have medicine in the name, because they are the most hot and growing topics. So here we have intelligent systems for medicine laboratory.
Well, that's a great story. And now here you are, like, let's say 20 years later?
20, right? 20 years later. So the largest lab, the largest bioengineering lab in Western Australia, probably one of the strongest in Southern Hemisphere. So all going well. Our mission statement is to develop and apply technologies to improve clinical outcomes. So we are very, very focused on actual patient outcomes. Many colleagues are telling me, so I have 2 medical institutes around me, that our work is closer to patients than anybody's in these medical institutes, but because these guys work only with mice. And we work with reality, with real people, and with real diagnostics, prognostics, and planning.
And I mean, how can robotics can be applied to the surgery or to the actual research?
Robotics has been around for a very long time now. And when I first attended my robotics conference, I was a PhD student at the time in Poland, and I think this was the conference was in 1992, called Romancy, Robots and Manipulator Systems one of the prestigious conferences in the field that was held at the time in Poland, in Krakow. I heard a keynote from a very famous American robotics researcher that in which he proclaimed that within 10 years, every Japanese household would have a domestic robot in their apartment, and every second American household would have an autonomous domestic robot. And it didn't happen. And 5 years later, I heard the same prognosis from a different keynote speaker, and 10 years later, again and again. So we need to ask ourselves a question. Why are we not surrounded by robots? Look through your window. Do you see any robots? No.
No.
The promises were that the university campus would be swarmed by robots by now, right? The problem is that robots work well in structured environments. So on the factory floor, where everything is set up, the robot is good. But in unstructured environment, robots fail completely. So we put the blame onto computer scientists who promised artificial intelligence and haven't delivered, right? So computers or computer-based control systems seem to have significant difficulty with uncertainty and unstructured environment. And this must be probably some very deep difference between how we operate and how computers operate. We cope with unstructured situations much better, and we can even deal with situations we encounter for the first time. There is no possibility currently for any computer system to deal well with the situation they encounter for the first time. So essentially, you can have a super intelligent computer playing chess or Go, but if you ask the same computer to play ping pong, there will be no chance. Or to play, for example, blackjack. So you need to reprogram or retrain if it is a neural network or deep learning system or something like this. And we somehow are able, better or worse, to play poker, chess, bridge, and if we are told to play blackjack, after a few minutes we will be able to play blackjack as well, even if we have not been trained before to play blackjack. So now if we translate this kind of situation to medicine and to surgery, you will see that, okay, hospital is a structured environment, which means you can have autonomous or automatic machines riding in corridors and delivering, say, drugs to patients or scripts to nurses and things like this. But when it comes to actually doing a surgery, you can't say it's structured anymore. So I think the idea that we can have autonomous surgery can safely be abandoned. I am very radical about it. So the robot can be used as a tool in hands of a human. Like, for example, Da Vinci robot, it's called a robot, but it's not really a robot. It is just what we call a copy manipulator. It copies the movements of a surgeon at a very small scale inside the body of a patient, right? So it does not do anything on its own. It just translates the motion and all thinking and decisions of a surgeon to precise manipulation at very small length scales, right? So this is, of course, very good. And then I'd like also to point out that there is very significant resistance, both on, say psychological and social aspects of the situation. Both the medical profession and the patients are not happy or ready to delegate decision-making to a machine, right? So no, that will not happen anytime soon. apart from perhaps some extreme environments, like for example, surgery on a space station where maybe you don't have access to human experience, or maybe on battlefield. But even on battlefield, I still believe that there is a better prospect for teleoperation, essentially that somebody is doing something and the actions of a doctor at base are copied by a machine on the ground, rather than a machine doing something autonomously or on its own.
Okay, yeah, totally. I mean, makes total sense. I think that we as a society might not be totally prepared in order to replace, if we can put it like that, like human interaction or human decisions for our robots, you know? So basically the robots that we're using or that are being used currently in the surgeries are strictly for just to be used as tools, right? And how precise are they, you know, when it comes to the movements, when it comes to translating the doctors or the professional job?
Mechanical engineers have done excellent job. So very, very precise. Very much more precise that can ever be achieved by a human, right? But imagine this. Precision surgery, you will, or say, call it microsurgery. We have our fingers, so how can we access micro dimension? We can't. But if we have a machine that allows us to do it in this at the scale, which is say 100 times bigger, so we do scale of motion like this, which is then translated to 100 times smaller, very precise motions by a machine in a very reliable manner. So this is all under control. This is not even robotics. This is just very clever mechanical engineering.
And when it comes to applying robots into surgical treatments, and whenever you are about, you know, let's say a doctor, whenever he's about to identify the problem or the pathology, how can robotics can be applied into this field?
Okay, so this is a good question. This is an important question because this is a question about diagnostics.
Yeah, sure.
And there would be at least 10 times more diagnostic procedure per every intervention. So it is a much bigger area than actual intervention, right? So diagnostics has been revolutionized by imaging, right? So I'm not going to talk about genetics and things like this because it's outside the scope of the topic of today's conversation. But say imaging. So you take X-rays, CT scans, MRIs, ultrasound, PET scans, whatever, right? And then people look at it, radiologists look at it, and this is the basis of diagnostics, right? Now, the amount of images taken is so huge that it becomes problematic for humans to actually look at these images carefully. So simply, there is not enough radiologists to look at all these images carefully. So you need a machine to look at images, at least as an initial screening, normal, abnormal, and things like this, to essentially allow human radiologists to look only at the selected part of all the images taken, right? So perhaps this is not part of robotics, but it's still part of say computer engineering. So all these artificial intelligence systems, the deep learning systems, which are very good at seeing things in medical images. And there is now pretty good evidence that at least in certain types of imaging modalities and pathologies, artificial intelligence or deep learning or neural network-based systems are more accurate than humans. in detecting abnormalities and diagnosing the condition. Right, and then to tell you to give you the scale, I think in China alone there is more well over 1 billion X-rays taken every year. So there are a lot of images to look at, and I think by far the biggest subset of all images taken, medical images, is chest X-rays in China, because they go every year to some kind of a health check which contains chest X-ray. So it's beyond humans to carefully look at all these X-rays. But apparently, computer-based systems now are very good at seeing abnormalities automatically in these X-rays. And of course, the reason is that there has been a lot of data already collected, and therefore there are a lot of data available to train these neural networks and or deep learning systems, or how you call them.
Okay, wow. I mean, I didn't know that. And okay, let's say that the robot or the model has already received all the information and processed all the information from the scans, from the images. How is that information presented to the surgeon?
So, as I said before, the main very important step is to actually not show anything to the surgeon when the image is considered normal and not there is nothing to worry about. That's the main thing.
Okay.
That a surgeon or a radiologist does not even see, because it's all good and we go to the next case, right? Because out of these 1 billion, say, X-rays, there will be 990 million probably showing nothing to worry about, right? So now the ones which have something to worry about are automatically normally labeled by the system. So they label, oh, look, machine says, I suspect tuberculosis. Or look, I suspect lung cancer. I'm still using that example of chest X-ray, right? So in my opinion, by far the most important thing is to essentially take the vast majority of images labeled as normal and not show to anyone.
Okay. Just making the scans makes total sense. Okay. Oh, really? Okay, nice. Yeah, makes sense to not
I've worked in Singapore in biomedical imaging laboratory, the government lab led by a great scientist, Wies Nowiński, also, by the way, from Poland. And they had a project assessing the normality of abnormality of brain MRI. You see, in Singapore, the amount of MR data taken was already problematic for radiologists on the ground to carefully look at all of them. So there was a problem. Okay, which brain MRIs can be classified as normal and therefore not shown, or at least not shown as priority to a human radiologist? And they came up with a very simple idea. Looking at the brain symmetry. Brain is approximately symmetric. But if you have some kind of a pathology like brain tumor or hydrocephalus or something like this, usually that symmetry is completely gone, because usually the brain tumor is somewhere on the left or on the right, right? So they developed measures of symmetry, and the brains which were symmetric, they were classified as good and not shown to human radiologists, or at least not shown at the top of the queue, right? Pushed back. Simple, and no artificial intelligence, no nothing. Simple algorithm measuring symmetry.
And I mean, since we're talking about improvements in the future, do you think that, let's say, in 30 years, we'll have a life filled with robotics, you know, like that every time that we get injured or whenever we go to the hospital, we will have a robot in there?
This is this question is about whether there is an inherent impossible to overcome difficulty with computers operating in unstructured environments, or whether it's just a matter of the power of the computer. And if you have a computer powerful enough, that computer will learn how to behave in unstructured environments like us, right? So this is a very deep or high level question, and there are a number of people, famous scientists, specifically, for example, Roger Penrose, the Nobel laureate in physics, who put forward, in my view, a very convincing argument that it is in principle impossible, right? Which means 30 years or 300 years or 3,000 years makes no difference. It is in principle impossible if you believe in that so-called Gödelian argument of Roger Penrose. And I actually believe that this argument is correct. And I have seen, I have worked in robotics for 30 years, and I have seen zero progress in this ability of robots to roam the streets, right? I have seen enormous progress in engineering development for industrial robots, or for image recognition, or for I don't know, localization and mapping and things like this. But for example, in self-driving car, I don't believe. I don't think this can happen. It can happen in China, where they will structure the road. Right, the road will be prepared for cars, but just self-driving on random road in Australian outback, no, I don't believe in such things. And I don't believe in such things not because I am thinking the technology is not mature enough, but I believe that there is in principle difficulty there. Essentially, that technically speaking, that many operations we conduct in our brain are non-computable. And of course, non-computable operations cannot be replicated on a computer because it computes. And if they cannot, then machine cannot traverse certain abilities we possess.
But let's be positive and let's hope for a brighter future when it comes to this industry. And also, I wanted to ask you, I mean, are there any projects that you're currently working on this path?
So we work mostly in using engineering and biomechanics methods to analyze images for prognosis and diagnosis. So our main area is planning for epilepsy surgery. This is a very important topic, because about 70 million people suffer from epilepsy, and probably about 20 or 25 million of them could be permanently cured by precisely targeted surgery. But the catch is precisely targeted. You need to know which part of the brain emits abnormal electrical signals that cause seizures, and you need to know precisely so that you can get there and get rid of that small bit, right? So our work is on that precisely targeting part, localizing that so-called seizure onset zone. Another project we work on, also related to brain surgery, is compensating for brain deformations during surgery. Brain is very soft, and if you start the operation, everything moves, which means your pre-operative MRIs do no longer correspond to the configuration of the brain during the operation. So you essentially lost your map. You plan your operation based on pre-operative MRI, but after you start the operation, that map is no longer accurate. So we need to know how the brain deforms during the operation to inform the surgeon where the surgical target has moved to. And the third big one is in vascular disease, aortic aneurysms. When they rupture, people die. But nobody knows which ones will rupture and which ones will not. So we use biomechanics to understand structural integrity of the aortic wall, and we are able to say which walls have structural problems and therefore are more likely to rupture, and which walls seem to be all good, so it can be left in peace.
And any last advice that you can give to our audience?
It's important to avoid working hard, because if you work hard, there is little time left for thinking, like on tangents, and good ideas usually come at unexpected times when you are on the beach or maybe in the dream or who knows what. So my main advice is to avoid working very long hours, because then there is no space for these thinking processes to naturally occur.
That's the best advice I've ever heard. Thank you, Professor, and thank you so much for taking the time of being here. We really enjoyed hearing your experience. Do you have any social handles where we can find you, or email or website?
Well, of course, my lab has a website and I have a website, but I categorically refuse using social media. No Facebook, no Twitter, no nothing. Well, I think the easiest is to Google Intelligent Systems for Medicine Laboratory. If you Google this, you will find it. And if you want my website, you just Google Karol Miller at the University of Western Australia.
Okay, really easy to find. Thank you so much, Doctor. And remember, guys, that you can also find more information, interesting articles, interesting interviews, just like this one, in our website, controlhub.com/builder-nation. We would love to hear from you. And thank you so much for being a part of this community. Thank you so much for your time, especially to the doctor here today, Dr. Karol Miller.
Thank you so much. It was a very pleasurable experience.